Good morning, everyone. In the last class, we were talking about NoSQL data management and the differences between NoSQL and relational data management (RDBMS), and why the name NoSQL and what it is doing other than no other. I mean, how it is benefit, how this can be get applied over relational databases. And we have discussed about a few more things like NoSQL as for NoSQL has four approaches. One is a key value store, the key value, and second one is like a column, and third graph database. And from this four, okay. So first one is like a document database model that you have discussed, a document database model, and second one is like key value store, and third relational data, and third one is the column family store, and fourth one is the graph database. So graph database is also called as node database. And next to that, we have discussed about materialized view. What is called material view is like a snapshot. And the next part will be talking about distribution model. So this is where we have left in the last class, right? So distribution model. And here this the advantage or the idea behind NoSQL is its ability is to run databases on a large cluster. And like depending on the distribution model that we choose or we select, we can handle the data store, and we can manage the different quantities of data. And here there are two data distribution techniques. One is called replication, other one is called sharding. So regarding this replication sharding, we have discussed in module 1 also, right? So replication, which takes the same data and copies it over multiple nodes. It is getting replicate, so which takes the same data and copies it over multiple nodes, whereas sharding, what it does is it puts a different data on different nodes. So it is a difference between replication and sharding, so which puts different data on different nodes. Even we this NoSQL has this approach called sharding, so which performs different data on different nodes. And these two approaches, these two techniques are orthogonal techniques. So we can use either any one technique, or we can use both the technique in our approaches. And here this replication comes in two forms. One is master slave, and second one is peer to peer. And we'll be studying from the beginning. We will be studying first we will be starting with a single server, and then master slave replication, and then sharding, and finally peer to peer replication. And since our syllabus, we have only one topic, we have only one technique in our syllabus, it is called sharding. So this alone we'll be discussing in brief. The other topics like single server, master slave replication, final peer to peer replication, we'll be just having a brief overview of it. Okay. So first, single server model, and this is the most traditional model. So this is the most traditional model. The first and simplest distribution option is the one that we recommend as single server. The reason is that here nothing is distributed, right? So nothing is distributed. The things will be getting running on a single machine, and which single machine handles all the reads and writes to the data store. So this option, this single server model is mostly preferred. The reason is that it eliminates all the complexities. Like we don't want to worry about the distributed clusters, we don't want to worry about the distribution, we don't want to worry about how the database will be handling the data. Since it will be running on a single machine, the complexities will be a little bit less. But one thing is, we can't apply this for data analytics like big data and these kind of huge applications. And even this SQL databases, with the idea of running a cluster, it can use NoSQL, the single server distribution model. And graph database, which you have discussed earlier, graph database are obvious or this category, and which works best in a single server configuration. So graph databases works best in a single server configuration. And this is about this is about single server model. The one thing to be get noted is single server model will not we don't have that much complexities as we have like in sharding and the other techniques. And since it is a single server model, that nothing is distributed, things will be get handled in a same system, like in a same machine, even both read and write. Okay. And second one is about like master slave replication, right? Before that, let us see what is called sharding. So And when you talk about distributed, and when you talk about a data set, the data set can be accessed by different people. Different people will be accessing different parts of a data set, right? So we'll not make sure that the data set will be accessed or will be get hold by only by a single person. So in these cases, in these cases, we have one technique called sharding, which supports horizontal scalability by putting different parts of the data onto different servers, which makes things to get handled a little bit easy. And here you can see this diagram, and here you can see like each shard reads and writes its own data. You can take this as like each shard which is reading and writing its own data. Just treat at like a single different three servers, and we have this three servers. Through three servers, these data are being communicated, this data are being sent out. Like shards put different node or different data on separate nodes, each of which does its own read and write. That is the concept of it, right? So like here we have different data on separate nodes, each of which does its own read and own writes. And whereas a single server model which will be doing all the things on a single machine. So when we have different users talking to different server nodes, then load balancing and handling the data queries is challenging, right? So like each user has to talk, and what is this we will be doing here is each user has to talk only one server, so it gets rapid responses from that server. In that way we can make these three things to be distributed. For example, if I have 3 to 4 servers, and I can segregate people, if a people is coming, if I can segregate people of group of like one first to 10 will be in first server, second 10 communicate to third, second 10 can communicate to second, similarly something like that. In this way we can arrange this and we can make the load to be even. And the other thing is like how to clump the data, so that like one user has to get the data from a single server, right? So one user has to get the data from a single server, is not going to talk or to communicate with the other servers. And again here the whole thing is aggregates, so which combine data that is commonly accessed together. So aggregate is the one which combines which combines the data that commonly accessed together. So here this aggregate, as I told you, like aggregate is like a bunch or unit of distribution, and again it is a distribution. And when it again comes like arranging the data and nodes, how to arrange the data and nodes, there are few factors. Like when you arrange the data and nodes, you need to look into performance, right? For example, if you want to place an order, as an example which is taken as, if you want to place an order in some other place like Boston some place, and you can place the data even in the US data center. It was one example for this. And another factor is like how to keep the load even, right? How to keep the load even. So this means that what we are trying to do is we should try to arrange aggregates, we should try to arrange the aggregates, we should try to arrange the units, so that there will be this will be evenly distributed across the nodes. So that you can make sure that all the missions will get equal amounts of the load. In some cases this may vary over time, in some cases you can see the difference, but mostly it works better. And in some cases it is useful to put aggregates together if you think to be read in a sequence. And here you can talk about a small example. And here we treat that we have three servers, like the servers will be handling the things like if when it is handling the queries of a server, the response of customers. So server 1 will be, server 1 will be server 1, server 2, server 3, and the customer surnames starting with A to D will be get handled by one shard, and E to G on the other. Similarly, remaining will be get communicated to each shard. Like this will be made as like a block. And even if I do this, the programming model again will be get complicated. So what I need to do to this is like to ensure that which is distributed across various shards should be rebalanced. If I'm rebalancing the sharding means I need to change the application code and I need to migrate the data. And even this NoSQL databases supports this auto sharding. What is called auto sharding, right? As I talking about, we have different customers, so that I take customers A and D will be responded by one shard, and customers D to customer surname, so starts with E to G will be responded by shard 2. And similarly the next let me take like H2K or H2L or M will be responded by the third shard, similarly just up to this. And how can I treat, I mean, like when I get a customer query, I need to know whether it is from the customer whose surname starts with E or B, and then I should match this to a particular shard. I should not make exchange the name, exchange, I should not make an exchange, I should not make the problem to be a little bit complex. So this part will be, I mean this scenario, this part will be get handled by the NoSQL database, that is called as auto sharding, where the database takes on the responsibility of allocating data to shards, and which ensures that data access goes to the right shard. I mean, if my first letter starts with this, if I'm trying to communicate with this, if I'm passing a query to my database, it should pass to certain shard. It will not be going to shard 1 or shard 2. So this is how NoSQL makes things little bit easier manner. Okay, and next thing, so sharding is valuable performance, like since it can improve both read and write performances. But whereas when you take replication, so it particularly treats with caching, you can improve read performance, but you cannot achieve that write performance in replication, since the data is getting replicated, and avoiding those avoiding those writes will be little bit complex. And this sharding provides a way to horizontally scale writes. And second thing, like sharding has the property like to improve resilience when used alone, and even when it is lead to any failure, even it is even one of the node is getting failure, this sharding will help you to decrease the failure rates will be decreased, performance can be get increased with this sharding. Okay, so this is about sharding. So sharding is particularly valuable for performance that we have discussed, and using replication, particularly with caching. This replication you can improve reading, but writes cannot be get improved with replication. But when you use this sharding, which supports both read and write, and in addition to this, even as I told you, this is an orthogonal technique. You can apply both sharding and replication can be applied together on a can be applied together in a distributed environment. I mean, you can apply both the techniques on the NoSQL database in processing it. Okay, so in practice, we prefer sharding alone is likely to decrease resilience. And the next one is called version stamps. So version stamps, what is the need of version stamp? What does it mean? Like when you start doing some kind of work or project, you can see version 1.0, version 2.0, version 2.5. It is something like that. So when you look into a database, like some databases, some databases lacks in supporting of transactions. So some supports a transaction are much better. When I talk about a transaction, and here there are two terms. One is business transaction, other one is system transaction. So let us come to that. What is called business transaction and what is called system transactions, for example. And there are some transactions which is being handled by the system, but some transactions are there which requires less human intervention, and which cannot run without human intervention. So these transactions will take some time period to executing it when comparing to the normal transactions. And to handle these cases, when it comes to like a single server distribution model or multiple list model, these things can be get handled with the help of version stamps. And let's see how it is helping to do these things. See, a business transaction is when user thinks about transaction. That means like mostly it will be business transaction. It is something like borrowing a catalog. I mean, it is something like borrowing a product catalog or choosing an item for and placing an order, and filling my credit card information and confirming the order. It is something like when I place an order in an Amazon site, right? So that is called business transaction. And here this is not working within the system transaction, right, which is provided by the database, because this would mean locking the database elements like credit card, some information of this. If it is like a system transaction, unless if I don't go for placing an order, I'm confirming order through payment, just I do the things, that is system transaction, which will be handling the entire things at the back. And usually these applications begins with a system transaction at the end of interaction with the user. They hold it holds for a shorter period of time. And the problem here is that calculations and decisions are being made based on data that's changed. I mean, the price list which updates the price of the item which you purchase, or someone may update the contact address of the customer, or the shipping charges will be get updated. So one is getting updating, it has to get reflected in all the others. And we have few techniques. Like the techniques for handling this are, one is offline concurrency, so which is used in NoSQL. And second approach is called optimistic offline lock. So it is a form of conditional update where a client operation rereads any information that the business transaction relies on and here to ensure this records in the database, we use version stamp. So it is a field version, as you like in C program, should have used a term called flag. In programming languages, you will be using a flag bit like 0 and 1, right? Similarly, it is like a version stamp, and it is a field that changes every time. That changes every time when the underlying data in the record changes. When you read the data, keep a note of the version stamp, so that when you write the data, you can see that the version is getting changed. For example, if the data is there, I'm trying to read it, one transaction is done, then it will be having the version as 1. And next time when I write some other data on that, I will be getting the version as 2. So in this way, this version stamp works, and this works with HTTP. And in HTTP, it is done with like e tags. So whenever you get a resource, the server responds with an e tag in the header, and this e tag is a string which indicates the version of the resource. So this e tag is a string which indicates the version of the resource. I shall show you a small example to this. And here you can see like one thing is called CAS, compare and set operations. So what this comparison set operation is doing, like it run against resource between the read and the update, and there are various versions to construct version stamps. So there are various things to construct a version stamp. One is using a counter. So using a counter, like always increment it when you update the resource. Just initial the counter as 0, count equal to 0 whenever this particular data field is being updated, which is being modified. Then you can keep on incrementing the counter. So it is one way of doing this version stamp. Okay. And second approach is GUID, having a unique ID to be guaranteed, like a random number that is guaranteed to be unique. So this uses some combination of dates, hardware information, whatever the other source of randomness they can pick. And the one thing about this is they can generate this can be generated by anyone, and it will never be get duplicated. And disadvantage is that they are large and they can't be compared for reasonness. And third approach is to make a hash of the contents of the resource, and we can use a hash key size, a content hash which can be globally unique, which can also be unique like GUID. And the advantage is that it is deterministic. Any node will generate the same content hash for same source, same resource and data. And the fourth approach is to use the timestamp of the last update. So that is the first approach, is use the timestamp of the last update. See how this works is like counters. This is reasonably short and can be directly compared for reasonless. But whereas multiple machines, when we work with multiple machines, can generate timestamps, and this timestamps can be get properly synchronized with the clock, right? This should be synchronized with the clock, so that you can make sure that whatever the message is being exchanged from one node to other node will be having its proper thing. And here you can see some vector stamp on multiple nodes, for example. And here you can see vector stamp is a set of counters, one for each node. And here a vector set for 3 nodes. One node is blue, second node is green, third node is black. And this looks something like blue 43 is the version, right? 43 is the version, and green 53, black 12. And each time a node is getting update, either internal update, when it is each time a node is getting update, it updates its own counter, so that you can see the green node which is updated as 55, and now it will change to the update vector as 55, whereas you can see the other blue 43, black 12 remains the same. Okay, so this version stamps help you to detect concurrency and conflicts. So when you talk about a conflict, when you read a data, when the other one is reading a data, it is not a conflict. See, read and write will not be resulting in a conflict, whereas write and read, if one is writing the data, other is reading the data, that results in conflict, and write and write results in conflict. So these conflicts can be handled by this vector stamps. Okay, so vector stamps help you to detect concurrency conflicts. When you read data, then update it, you can check the version stamp, and it ensures that nobody updates the data before you read or before you write. Once if it gets the updated information, the version will be get updated. And second thing, version stamps can be implemented using 4 approaches, right? One is using counter, second using GUID, third using content hash, fourth using timestamp. So timestamp should be always synchronized with the current system time. And next one is like with distributed systems, we can use version stamps, which allows you to detect when different nodes have conflicting updates. So this helps you to avoid conflict updates. And the next one is called MapReduce. See, MapReduce is so when we talk about big data, I can talk about Hadoop, right? I can talk about Hadoop, and it is not like we are going to discuss in brief about what is called MapReduce and how it works in MapReduce in data analytics. So we'll be just studying about, we'll just having a flavor of MapReduce, how it's being supporting in databases, how it works with aggregate oriented databases. That is what we will be doing. And since like MapReduce is one of the technique, or MapReduce is something like it is a way to organize it is a way, or it is a MapReduce can be implemented on a Hadoop platform. See, MapReduce has concepts, right? MapReduce has concepts like map method, combine method, reduce method. Those methods can be get implemented on in a functional programming language like Java. So the MapReduce is a pattern to recognize processing in such a way to take advantage of multiple machines on cluster. To be simple, it is a parallel processing, like things executing in a parallel manner. So when you have a cluster, there is there is few things to get immediately. You can have lots of machines to spread the computation over. So you can make things to be get achieved in the same time. You can which process the things in multiple missions. Okay, so the MapReduce pattern is a way to organize processing in such a way as to take advantage of multiple missions. And the one thing is like Google's MapReduce framework, that you can take an example of this. See, as the name like a MapReduce, it reveals its inspiration from the map and reduce operations on collections in functional program languages. And let us have a small example to it. And if you take MapReduce in other textbooks like in Hadoop or big data textbook, you can see map method and reduce method, and you can see 5 phases of MapReduce. As an example, you can see finding the frequency of word counts in a given text file. But whereas here what we do is the same, logic will be same, but we'll be having a small flavor added to it. Okay, so just let us start with a basic MapReduce. And let's assume that we have chosen orders as our aggregate, and with each order having line items, and each item has a product ID, quantity, and the price tag. Okay, so this aggregate when it wants to process the whole order in one access, and if you have a lot of orders in doing the things. So like let us take a small example, even if it is not understandable, let us take a small example as Amazon, right? So Amazon has a number of orders. Amazon, like a number of customers are placing their orders in Amazon in a minute. And when I want to track the number of orders being placed in a particular day or being placed in a particular month, then I need to track the order IDs which are placed by all the customers, like. So then I need to do it then if I do it like in a serial manner, then to solve this it will take much more time. But when I do this the same thing with in a parallel manner, that can be done in an easier way. So that can be done with the help of this MapReduce. And here we have different stages. The first stage is a MapReduce job. So let me take it simple. So let us take this small example for understanding, right? So you want to count the frequency of words from a given text file. So it is a given problem. First, what we do is we need to map, and we need to map a function. First we need to map a function. Then mapping means like for the given set of file data. First you need to map, then you need to start counting it, then you need to start counting it then you need to reduce it. You need to reduce it means like it is something like a divide and conquer strategy. You will be just dividing the problem into sub problems, so that by solving the sub problem you can make the original problem to be get solved. It is something like that. And here this map is a function whose input is a single aggregate, and this output is a bunch of key value pairs. As I told you, like a key value pairs, the meaning of this is I told you a small example. Even this concept is there in dictionary in Python. So key value pair. So like for example, let me take a text file. In the text file there is a string called hello, how are you, hello. So as a result, I can see hello is repeated twice. Hello will be the key, value will be 2. How will be the key, and the number of times it has occurrence is 1. Similarly, I can see R, I can see U. So it is something like a key value. Name will be the key and your name will be the value. Age will be the key, 12 will be the value. It is called a key value pair. So in this case, the input would be in an order, the output will be then this key value pair. And let us see that small example. See, this is a small example. What it is doing is, it is a map function reads records from the database and emits key value pairs. And here if you take it, that is one we have ID, and second you have customer, and third you have line items. Okay, so one we have ID and second you have items. One, just give me a minute. Okay, so first we have ID customer. So since we are doing with line dot items, we have 3 customers, like we have 3 customers, and now I need to trace the IDs. I need to trace what is being purchased by this particular customer. I mean price and quantity. You can see like this is a map function which splits. This is which splits means you can see the first customer 1 and the item which is purchased by customer 1, price and quantity. Similarly customer 2, similarly customer 3. So it is a map function reads record from the database and emits key value pairs. And here you can see this price as a key and this $26 as a value. Okay, so each application of the map function is independent of the others. It will be doing like in a parallelizable manner, so that you can do the things in an efficient manner. Okay, so a map operation only operates on a single record. A map operation only operates on a single record, and the reduce function takes multiple maps out with the same key and combines the values and combines those values. So while the map function is limited to working on a single data aggregate, the reduce function can work on multiple aggregates for a single key. And here, right, so a map operation can only operate in a single record. That's what we're talking about, right? So the reduce function see, the meaning of reduce is reducing 1 to 1. So divide and conquer problem for a given problem. As I told you, like a small word frequency ones, it is also same thing. And here you can see the name of a customer 1 pure, and you can see price quantity. Totally he has placed 3 items, and totally his price is $26, $36, $4, and he has placed for 3 quantities. So once after doing this, I need to know how many number of quantities has being placed by this particular customer. So I can see the reduced part of it. I can see all the 3 things which is reduced part of it. See, earlier what you have done is the most common problem, the given problem is splitted into sub problems, right? The given common problem is splitted into sub problems. Once after doing that sub problem, then what I'm doing is I'm going to merge. I'm going to combine and merge. I'm going to reducing it. That is what reduce. The reduce function takes several key value pairs with the same key and aggregates that into one. Bunches it into a one. So the map reduce framework arranges for map task to be run on the correct nodes to process all the documents and for data to be moved to the reduce function. And here you can see like a partitioning and combining. So in simple like map reduce job, you can see a single reduce function. The outputs are various nodes concatenated together. And here as I told you, like if it is a single task, then it is simple. If I'm doing it, since I'm doing it on a parallel manner, I can see multiple partition data. So I can see multiple partition data. I can see a customer like a pure, I can see the same customer like a pure 44, and simply like what map is doing is the given thing, map is splitting. It is splitting it and combining things from this to this and combining things from this to this. And now it is combining and reducing the result. So it is combining and reducing the result. So it is called like a partitioning. So partitioning allows the reduce functions to run in parallel on different case. So it is a combiner function. As I told you, like combiner function, it is a reducer function, like which combines as the final reduction. It is a final reduction stage. The reduction function needs a simple special shape. So it is a combinational reduce. You can see it, entire thing is reduced into a single value or a single key. Okay, so but like let us see how this further is. So it is the reduce function which counts how many unique customers order a particular tea. It is not combinable. So even you can make the things you can filter the things in a way that we need to calculate, that we need to compute it, right? So it is of map reduce. And composing map reduce calculation. So the map reduce approach is a way of thinking about concurrent processing, how you structure your computation for in a straightforward model for parallelizing the computation over a cluster. So within a map task, how you can operate on a single aggregate. Within a reduced task, how I can operate on a single key, and what are the other limitations of this. Like one example for this, you can take calculating averages. So let's consider that the kind of orders we have been looking at so far. Suppose we want to know the average order to quantity of each product. I need to know the average order to quantity of each product. And important property of this average is that they are not composable. I mean, if I take two group of orders, I can't combine their averages alone. I can't combine their averages alone. Instead, what I should do is I need to take the total amount and the count of orders from each group. At last, then I can go for average. So here if you look into it, total quantity 600, total quantity 600. When I need to go for an average, what I should do is first I should combine this total quantity into a single and reduced total quantity. Then I can take an average of it. That is what the logic of it when calculating averages. And you can see this in next slide. So this map is doing three quantities and it is reducing it a single quantity. So which makes a count, each map emits one and which sign is submit to a total. Okay. And the better way of understanding this map reduces, and let us take that I've given you a storybook. I've given you a storybook, or I've given you some kind of storybook, and I want you to count the frequency of the word bird, BARD. I want you to count, and I was given a storybook related to bird, and I want you to count the frequency of word bird, how many number of times it is being occurring throughout the textbook. And if I ask you to count for a single page, then you will not be looking for someone's help, right? You will not be looking for someone's help. You can do this on your own, and you can tell me how many number of times it is repeating. So it is like a single server. It is like a single. It is not a distribution. It is a single model. And if I ask you to do for entire textbook, if that textbook is combined, if that textbook consists of nearly some 2500 pages, so a textbook of 2500 pages, you need to count the number of times the word bird is getting repeated throughout the entire textbook. And if this is the given task to you, now you can't do this task on your own, right? You need help of someone. I mean, like you can get help of your friends, so that you can have some 5 to 6 friends or 10 friends. So one friend, the first person can count the frequency of word bird from page number 1 to 10. Second one can be count from page number 10 to 20. Third one can be count from page number 30 to 40. Fourth one 40 to 50. Similarly, until you cover the complete set of pages. This is called map. Okay, this is called map. Giving how the problem can be mapped into a key. This is called map. And now what I'm trying to do is, and now I need to get the result. Now what I will do is, now I will be combining. I mean, what is a person 1, person 2, the result of person 1, person 2. For example, person 1 result will be bird, number of times it is occurring on page number 1 to 10 is 15, and person 2, number of times it is occurring from page number 11 to 20 is 60. So similarly, I need to combine 2. I will be combining 2 to person A, person 1, person 2, person 3, person 4. Similarly, in the next step, I will be reducing further. This is called reducing, right? This is called reducing. In the next step, I will be reducing further, and I will be combining. At last I can see if I combine this, at last I can see the single answer, like bird, the number of counts will be some nearly like let it be some 18,000, let it be some 18,500. So it is a number of counts that I got from the complete set of students, complete set of guys. So as a result, when I get into a result, I can see everything will be get combined. So it is called a map phase, it is called shuffle phase, it is called reduce phase, it is called combine phase. Okay, so these are the phases in MapReduce. It is the logic behind MapReduce programming. So MapReduce programming is MapReduce programming is not a platform. Hadoop is a platform where you can execute this MapReduce programming concepts in a language called Java. like you can use this concepts like map function, reduce function, and those functions can be get implemented and can be executed. You can use either Java or you can use Python. Even we can work out with this NoSQL with Python. This supports better. So this is the idea behind MapReduce. And what is the difference between MapReduce and Hadoop? Hadoop is a platform which helps you to implement your algorithms, which helps you to run your algorithms, run your languages on this platform. Okay. So MapReduce is a pattern to allow computations to be parallelized over a cluster. Second thing, MapReduce operations can be composed into pipelines, as I told you, like map and reduce. So reduce the input to another operation, map, and result of MapReduce computation is widely used, which can also be stored as materialized, which I discussed earlier. So materialized use can be updated through incremental MapReduce. Okay. So as I told you, like when I come out this entire solution as in bird, I can see bird. I can see some value of a bird like a 123. In this is called key, and this is called value, and it is called key value pair when I come out as like a result. Okay. So this is up to MapReduce computations. Thank you.